We will now review vector multiplication. The first one we will look at is scalar or dot product. Here we have two vectors with an angle theta between them. The dot product between these two vectors is written A dot B, and it's defined as the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. It is referred to as the dot product because of the symbol used here, or as the scalar product because the result is a scalar. Let's first look at the dot product between unit vectors in the Cartesian coordinate system. So the dot product of AX with AX will be the magnitude of AX, which is 1, times the magnitude of AX, which is 1, times the cosine of the angle between them, which is 0 degrees. And since the cosine of 0 is 1, the result will be 1. So the dot product of a unit vector with itself is 1. Let's look at the dot product between two different unit vectors. So the magnitude of AX is 1, the magnitude of AZ is 1, and the angle between them is 90 degrees. Since the cosine of 90 degrees is 0, the result will be 0. So the dot product between any two different unit vectors is 0. With what we know about the dot product between unit vectors, let's look at the dot product when we have the vectors in component form. Distributing this, it will become, so this term dotted with this term is ax bx a sub x dot ax. This term times this one is ax times by, and then an ax dot ay, and so forth to get these 9 terms. So the dot product between any two different unit vectors is going to be 0. So these terms are all 0. These remaining dot products here are going to be 1. So the result for A dot B will be AX BX plus AY BY plus AZ BZ. So here's how you would take the dot product if you have your two vectors in component form. So if you were to take the dot product of a vector with itself, you would get a sub x squared plus a sub y squared plus a sub z squared. So that would just give you the magnitude squared of the vector. So a method for finding the magnitude of a vector is taking the square root of the dot product of the vector with itself. Another use of the dot product is to find individual components of a vector. So for instance, if we have a vector A and we wanted to find the component in the y direction, a sub y, we would dot our vector with the unit vector in the y direction. So ax dot ay is 0, ay dot ay is 1. So you'd be left with a sub y. And finally, ay dot az is 0. Here are the commutative and distributed laws of vector dot product multiplication. You can verify these two expressions by writing out the vectors in component form and evaluating the two sides of each equation. The dot product makes it easy to describe physical phenomenon. For instance, let's say we have a capacitor, and we'll talk a lot more about capacitors later, and we charge the capacitor so that we have a uniform electric field intensity inside the capacitor as shown. If we place a charge Q inside the capacitor, it will experience some force, and that force will be equal to the charge times the electric field intensity. Let's take that charge and move it along this path, which I will call L, and there will be an angle of theta between the electric field intensity and the path we're taking. So it takes work to move Q along L because the electric field is pushing the charge to the right. Later we will show that the work it takes to move that charge along L is equal to minus Q times the magnitude of L times the magnitude of the electric field intensity times the cosine of the angle between our displacement L and the electric field intensity. This term right here is just the dot product between the electric field intensity and our displacement L. So the work is equal to minus Q times the dot product between the electric field intensity and our displacement. So we will find use for the dot product in describing physical phenomenon such as moving a charge around in an electric field.